Alrighty. So good morning, everybody. Welcome back. Those of you who have been gone for the last couple of weeks, like myself, welcome back. It is nice for me to be back in the classroom and to see students. I hope you all had a great weekend, that you got to actually relax and you didn't have to work or do school stuff all weekend, that you got some time to do something that was fun. And you know, hopefully it was a good weekend. So today we will be starting chapter 11 with our section 11.1. We'll get to that lesson here shortly. First, I want to show you some things that have been updated in Canvas. So I'm going to share my screen and look at the Canvas course. There we go. Alrighty here, so we have our Canvas course right here. This is what it should look like for you guys. In the modules, I've added some stuff and created a new module in there, a couple new modules. So first, in the things you might need, I have added some of the presentation on how to kind of get ready for the digital exams, for the AP exam. If you need that, that is available. I also have the PowerPoint presentation that was the review of all the chapters we've covered so far that I did last week, that we didn't have time to finish it all in class, so the entirety of the presentation is right there in the things you might need module. Next, I added these AP classroom review materials. Right, these are recordings of review sessions that AP and the College Board put together, and they're all ready right now because the first administration of the AP exam for stats is actually like next week, which is why we're not taking that one, because we're not quite ready for it, but all the materials are ready for review. So I have linked all of these videos. These videos are actually YouTube videos as opposed to the normal AP Daily, AP Classroom videos that are posted, that I put on here, that are actually inside AP Classroom. So you should be able to view these more easily. But they are broken down by topic areas, like content areas. They are longer than the AP Daily videos though. Like the AP Daily videos are usually like 8 to 15 minutes maybe. These are all like 45-minute long videos. They are more in depth than the AP Daily videos. They cover a little bit more content, and they're made to help you review. Okay, so those are now available and linked in the course. So if there is a specific area that you're really struggling with, these might help. All right, and then we finished up chapter 10. That's all the stuff for chapter 10 there. I'm combining the last 3 chapters that we're covering in the textbook into our last unit. So that's covering chapters 11, 12, and 3. There's a couple of benefits to doing this, hopefully benefits. One is that there will be only one more free response and one more multiple choice assessment for the whole semester. All right, and I'll combine these 3 chapters into a single pair of assessments. So that should make, as we get to the end of the semester here, there's not going to be a whole lot more added as far as things you need to do for the course. All right. The other side of the coin is there's just a lot more content within those assessments. I'll do my best to keep them the same length, but I need to make sure and assess the 3 different chapters. So everything for the last 3 chapters will be in this last module. It'll still be very similarly organized, where we'll have our notes and resources, practice problems, and such in here. I have our notes and resources for chapter 11, 11.1, and 11.2. There's only 2 sections in chapter 11. There's only 2 sections in the last 3 chapters. Each one has 2 sections. So in our notes and resources here, I am working on the study guides and the practice problems. Those should be ready by the end of this week. However, the rest of the resources that are normally in here, like the presentation for today's lesson on 11.1 from the textbook, AP Daily videos having to do with this content are all linked and ready to go. The examples from the textbook are all linked and ready to go. And the directions for how to do some of these procedures on your calculator are here, as well as where to find this content in your textbook. All right, so the normal, most of the resources are ready for you for Chapter 11. I'm just working on the study guides and practice problems still. All right, but those things are ready. All right, so there's some new stuff in there. Please, again, use the resources that are available. There's a lot of things that I cannot go over in our live sessions. We just don't have time. So I try to have lots of extra resources in the course for you. Hopefully that's helpful. All right, so then with that, we're gonna get started on our lesson. So if you're taking notes, now's the time to get that ready. We're gonna get started if this wants to cooperate. There we go. All right. So here we go, Chapter 11, Inference for Distributions of Categorical Data. Most of what we've done previously was having to do with quantitative data, right? Where we have shape, center, spread, those types of things. And we can do comparisons based on means and standard deviations and things of that nature. Categorical data, we can't have those same data points, so we have different ways to compare them. That's what we'll learn in this chapter. We're going to do first the chi-square tests for goodness of fit. We'll get into what that means shortly. All right, so in this lesson, we're going to learn how to state appropriate hypotheses and compute expected counts for a chi-square test of goodness of fit. We're going to calculate the chi-square statistic, degrees of freedom, and p-value for a chi-square test for goodness of fit. We're going to perform a chi-square test for goodness of fit, which is essentially just doing all the things in those first two check marks. And then not included in this lesson, which we will cover later, doing the follow-up analysis when the results of a chi-square test are statistically significant. I'm not sure why they included it on the objectives when it's not part of the slides, but we'll get to that. All right, so this is what we're hopefully going to cover today. Well, we will cover, we have time. All right, so sometimes we want to examine the distribution of a single categorical variable in a population. That is when we use the chi-square goodness of fit test. It allows us to determine whether a hypothesized distribution seems valid. So if we have a single categorical variable in a population, like we're going to look at an example that deals with colors of M&Ms. Color is our categorical variable. We have a distribution of the colors in our bag of M&Ms. Right, our chi-square goodness of fit test allows us to determine whether or not the hypothesized distribution or proportion of each color of M&M is valid. We can decide whether the distribution of categorical variable differs for two or more populations or treatments by using a chi-square test for homogeneity. We will not be doing that in today's lesson. This gets to comparing populations, two or more populations or treatments. Another lesson. We'll often organize our data in a two-way table. It is also possible to use the information in a two-way table to study the relationship between two categorical variables. The chi-square test for independence allows us to determine if there is convincing evidence of an association between the variables in the population at large. So our chi-square test can be applied to three different situations and used in three different ways. Whether we're comparing a single categorical variable and whether or not the claim of its distribution is valid, chi-square goodness of fit test. If we're comparing two populations, right, with categorical variables or two treatments, then it's a test for homogeneity. If we're checking for an association, or we can, they call it a test for independence, right? Whether or not one variable has an effect on another variable, if there's an association between the two, or if they are independent, they don't have an effect on either on each other. That's the chi-square test for independence. Today we will only be doing the chi-square test goodness of fit. Okay. So here's an example. Mars Incorporated makes milk chocolate candies. Here's what the company's Consumer Affairs Department says about the color distribution of its M&M's milk chocolate candies. On average, the new mix of colors of M&M's milk chocolate candies will contain 13% of each of the browns and reds, 14% yellows, 16% greens, 20% oranges, and 24% blues. In this case, our category is colors. Right. The one-way table summarizes the data from a sample bag of M&M's milk chocolate candies. In general, one-way tables display the distribution of a categorical variable for the individuals in a sample, such as the one below. We have our color, which is our category here, our categorical variable, right, across the top, and the count of each of these colors that we observed in our sample of 60 candies. Right, notice we are recording the count and not the proportion. This is very important. When we're doing chi-squared tests, we are concerned about the count, not a percentage. Although we could calculate the proportion, which allows us to compare to the proposed or claim of the proportion, right? And we have a sample proportion of blue M&Ms that is p hat equals 9/60, which is equal to 0.15. Okay. Here's that same table at the top of the screen now. Since the company claims that 24% of all M&M's milk chocolate candies are blue, we might believe that something fishy is going on. We could use the one sample z-test for proportion to test the hypotheses. The null hypothesis that p is equal to 0.24 and the alternative that p is not equal to 0.24, where p is the true population proportion of blue M&Ms. We could then perform additional significance tests for each of the remaining colors. Okay, that's one option. Performing a one sample z-test for each proportion would be pretty inefficient and would lead to the problem of multiple comparisons. Meaning maybe we get a significant result from comparing one proportion, but then in the next one we don't. And then maybe on the next one we don't again, and then the next one maybe we get significance. But with all of the different results, how do we make a conclusion? It just gets muddled. So we have an alternative. Okay. Performing one sample z-test for each color wouldn't tell us how likely it is to get a random sample of 60 candies with a color distribution that differs as much from the one claimed by the company as this bag does, taking all the colors into consideration at one time. That is what our chi-square goodness of fit test allows us to do. We can consider all of the colors, right? All the values from our categorical variable at the same time, right? And so we need to write our hypotheses a little differently. Now, the null hypothesis in a chi-square goodness of fit test should state a claim about the distribution of a single categorical variable in the population of interest. In this example, the null hypothesis is that the company's stated color distribution for M&M's milk chocolate candies is correct. Right, notice we're not like defining a parameter here. We're just stating we think that the company is correct. That's our null hypothesis, the hypothesis of no difference. The alternative hypothesis in a chi-square goodness of fit test is that the categorical variable does not have the specified distribution. So we write the same exact thing essentially for the alternative hypothesis, except at the end we say is not correct instead of saying is correct. Right? This is a little bit more efficient than trying to write out all the parameters equaling to a proportion and then saying in the alternative that some of them are not correct. This is just easier. Right? So our alternative is the company's stated color distribution for M&M's milk chocolate candies is not correct. Does anyone need a moment to write anything down so far? Do we have any questions? Raise your hand. We could also write the hypotheses in symbols as H sub 0 such that P of blue equals 0.24, P orange 0.2, P green 0.16, P yellow, P red, and P brown, as they're listed there. And the alternative would be at least one of the P sub i's is incorrect. If one is incorrect, then at least another one is as well. So, because obviously if one is not that proportion needs to be made up somewhere else, right? And again, the I in P sub I just is a placeholder for whatever we have in a subscript within the null hypothesis. Where P color is the true population proportion of M&Ms, milk chocolate candies of that color. So you could write your hypotheses in this way. In my opinion, it's a little bit easier to write it the way we saw on the previous screen. The idea of the chi-square goodness of fit test is this. We compare the observed counts from our sample with the counts that would be expected if the null hypothesis is true. The more observed counts differ from the expected counts, the more evidence we have against the null hypothesis. That's the basic idea. How much difference do we have between what we saw and what was expected? Assuming that the color distribution stated by Mars Inc. is true, which is our null hypothesis, 24% of all M&Ms, milk chocolate candies produced are blue. For a random sample of 60 candies, the average number of M&Ms should be, blue M&Ms should be 0.24 times 60, which is equal to 14.4. This is our expected count of blue M&Ms. We've done processes similar to this when dealing with random variables and finding the what is it called exactly? It's a distribution of the probability distribution, there it is, right? Where we multiply each possible outcome that the random variable could take by the probability of it happening. Same idea applies here. Right? Using the same method, we can find the expected counts for the other color categories, which is shown here. Orange, we would expect to see 12, green 9.6, yellow 8.4, red 7.8, brown 7.8. Right? So these are the expected counts we would see if the null hypothesis is true. We can compare these side by side, observed versus expected, in another table here. Right? And based on this table, we see a difference. Right? 9 is not the same as 14.4, 8 is not 12, 12 is not 9.6, right? All of these are slightly off, right? They're not really terribly close for most of them either, so we have evidence to kind of continue at this point, right? If at first we make our comparison between observed and expected, and it's like it's what we expected to see, there's probably not a whole lot of motivation to actually do the test, because we're probably not going to find evidence for the alternative. To see if the data give convincing evidence against the null hypothesis, we compare the observed counts from our sample with the expected counts, assuming the null hypothesis is true. If the observed counts are far from the expected counts, that's the evidence we are seeking. Right? We can compare these things using a side-by-side bar graph with each of the categories, and we can clearly see that the bars are not the same height between observed and expected, which we also saw in the previous table. Right, we see some fairly large differences between the observed and expected counts in several color categories. How likely is it that differences this large or larger would occur just by chance in random samples of size 60 from the population distribution claimed by Mars Incorporated? So essentially, this question, how likely is it that the differences this large or larger would occur, is essentially the same question we've asked in our other tests. How likely is it that we see what we saw in our sample if the null hypothesis is true? That's what our p-value represents. Okay, so again, we're not going to be finding p-value using this test. To answer this question, we calculate a statistic that measures how far apart the observed and expected counts are. The statistic we use to make the comparison is the chi-square statistic. Essentially, this is kind of like finding the standard deviation for categorical data. It tells us how far away from what we expect things are, which is essentially the same purpose as our standard deviation in quantitative data. Right? Statistic we use to make the comparison is the chi-square statistic. And that is this formula here. The chi-square statistic is a measure of how far the observed counts are from the expected counts. The formula for the statistic is chi-square, and chi is a Greek letter, it looks kind of like an X, equals the sum of the observed minus the expected value squared divided by the expected value, where the sum is over all possible values of the categorical variable. All right. And these observed and expected are counts. The observed counts and the expected counts. Again, these are not proportions or percentages. If you use proportions or percentages here, you will probably get something wildly incorrect. The table shows the observed and expected counts for our sample of 60 M&Ms milk chocolate candies. Calculate the chi-square statistic. So here's our counts, as in the table we saw previously, and this is the calculation of our chi-square statistic showing where each fraction, essentially, that we're adding up came from. Right, we have our blue box here of 9 and 14.4, so we get 9 minus 14.4 squared divided by 14.4. Right, the next one is 8 minus 12 squared divided by 12, and so on. The order in which these are all added up doesn't matter. I could do them in the opposite order. I can change it, you know, as we can with categorical data. I can switch it around. My results should stay the same. Okay, so if I started with what's in the red box and then the green box, the yellow box, blue box, and so on, and change the order that I added these, I'll still get the same answer. Right, we get approximately 10.180 as our chi-square statistic. Right, so essentially, we have standardized how far away we are from our expected values for each color. Right, think of chi-square as a measure of the distance of the observed counts from the expected counts. Large values of chi-square are stronger evidence against the null hypothesis because they say that the observed counts are far from what we would expect if the null hypothesis were true. Small values of chi-square suggest that the data are consistent with the null hypothesis. Again, very similar to how we've seen a standard deviation play out. Large standard deviation means more spread out. Small standard deviation means less spread out. Does anyone need a moment to write anything down? Or does anyone have any questions? Is there anything I can clarify so far? So now that we have a test statistic, we need to be able to find a p-value. The chi-square distributions and p-values. The sampling distribution of the chi-square statistic is not a normal distribution. It is a right-skewed distribution that allows only positive values because chi-square can never be negative. When all expected counts are all at least 5, very similar to our large counts condition that we've seen previously, except now it's 5 instead of 10. The sampling distribution of the chi-square statistic is close to a chi-square distribution with the degrees of freedom equal to the number of categories minus 1. Okay, so we're dealing with degrees of freedom again. In this case, degree of freedom is categories minus 1. It has nothing to do with the sample size. It has to do with how many, like in this case, how many colors were in our category. We had 6. Right? Remember, when we're dealing with degrees of freedom and like means and our t-test for means, it's the sample size minus 1. This is now number of categories minus 1. Right? So again, the chi-square distributions are a family of distributions that take only positive values and are skewed to the right. A particular chi-square distribution is specified by giving its degree of freedom. The chi-square goodness of fit test uses the chi-square distribution with degrees of freedom equaling the number of categories minus 1. The chi-square distributions is table C in our little tables and formulas packet. So now we've used all the tables. Right. We computed the chi-square statistic for our sample of 60 M&Ms to be chi-square equaling 10.180. Because all of the expected counts are at least 5, the chi-square statistic will follow a chi-square distribution with degree of freedom equaling 6 minus 1 equaling 5 reasonably well when the null hypothesis is true. And so we see here is our chi-square distribution with degree of freedom 5. Our chi-square statistic 10.180 lands here, and we have the shaded area to the right is our p-value, the proportion under the curve greater than that value. To find the p-value, we use table C and look at the degree of freedom equaling 5 rho. Okay, so here's a little excerpt from the table here. We have degree of freedom 5 in this row. All right. The 10.180 will land between two values. So very similar to how we use table B. Right, our p value is going to be in a range between two proportions, right? It's not going to be exact using the table. Right? And so our p value is between 0.05 and 0.1. So since our p value is between 0.05 and 0.1, is greater than alpha equaling 0.05. Okay. Now, just nowhere throughout the problem did we say use a significance level of 0.05. Whenever it is not provided, always default to using alpha equaling 0.05 for your significance test. If they don't tell you what to use alpha equaling 0.05. If they tell you what to use that one. Therefore, we failed to reject the null hypothesis. We don't have sufficient evidence to conclude that the company's claimed color distribution is incorrect. All right, so we find our expected values. We compare those to our observed values. We find our test statistic, our chi-square statistic. Then we use table C to find a p-value, and then we make our conclusion. But wait, there's more. So when we're carrying out a test, right, we have conditions just as we have for all of our other tests. And essentially it's the same conditions we've seen previously. Our conditions for performing a chi-square test for goodness of fit is that it is at random. The data came from a well-designed random sample or from a randomized experiment. We have the 10% when sampling without replacement. Check that our sample size is less than or equal to 10% of the population size. And our large counts, which is that all expected counts are greater than 5. That is expected counts, not observed counts. So the expected counts based on the null hypothesis being true. Before we start using the chi-square goodness of fit test, we have two important cautions to offer. The chi-square test statistic compares observed and expected counts. Don't try to perform calculations with the observed and expected proportions in each category. When checking the large portion, be sure to examine the expected counts, not the observed counts. Please remember these things. Does anyone need a moment to write anything down? Raise your hand. So this is the process in a nutshell here, carrying out a test. Right? Once we've checked conditions, suppose the conditions are met. to determine whether a categorical variable has a specified distribution in the population of interest expressed as the proportion of individuals falling into each possible category. Perform a test of the null hypothesis. The stated distribution of the categorical variable in the population of interest is correct. And the alternative, the stated distribution of the categorical variable in the population of interest, is not correct. Right? And how that's worded and what's included in there depends on your context. Start by finding the expected count for each category, assuming that the null hypothesis is true. Then calculate the chi-square statistic, given here, where the sum is over the k different categories. Right? K is just a variable placeholder for the number of categories. The p-value is the area to the right of chi-square under the density curve of the chi-square distribution with k minus 1 degrees of freedom. And again, k is the number of categories. I'm sorry, yeah, number of categories. So we need a moment to write this down. So here's an example. Going through an entire process, a test for equal proportions. Right, so here's our problem. In his book, Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, since January 1 is the cutoff date for youth leagues in Canada, where many NHL players come from, players born in January will be competing against players up to 12 months younger. The players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, judged by whether a player makes it into the NHL, a random sample of 80 NHL players from a recent season was selected and their birthdays were recorded. The one-way table below summarizes the data on birthdays for these 80 players. Right, so each quarter, right, our months have been cut up into quarters here, so I have 4 categories. Right, January through March, April through June, July through September, October through December, and we have a count, an observed count for each category. Do these data provide convincing evidence that the birthdays of all NHL players are evenly distributed among the 4 quarters of the year? Notice we are doing our 4-step process: state, plan, do, conclude. That is needed whenever you do inference. So state, we want to perform a test of the null hypothesis. The birthdays of all NHL players are evenly distributed among the 4 quarters of the year, and versus the alternative, the birthdays of all NHL players are not evenly distributed among the 4 quarters of the year. No significance level was specified, so we'll use an alpha equaling 0.05. That is our statement. This is what we are going to do. Plan. If the conditions are met, we'll perform a chi-square test for goodness of fit. Checking the random condition, the data came from a random sample of NHL players. That was told in the description. 10% condition. Because we are sampling without replacement, there must be at least 10 times 80 equaling 800 NHL players. In the season, when the data were collected, there were 879 NHL players, so we are good to go. Right, large counts. If birthdays are evenly distributed across the 4 quarters of the year, then the expected counts are all 80 times a quarter, which is equaling 20. These counts are all at least 5, so again, we're good to go. Our large counts condition has been met. Next, we do some math. We have to calculate our test statistic, our chi-squared statistic. Right, and we get chi-squared equals our observed for the first quarter, 32 minus 20 squared divided by 20. 20 minus 20 squared divided by 20, 16 minus 20 squared divided by 20, 12 minus 20 squared divided by 20, we get ultimately 11.2. Here's a graph of our chi-square distribution with degrees of freedom equaling 3, because 4 minus 1 is 3. We have 4 categories. Right, our chi-squared statistic lies right here. And this little sliver is our p-value, the proportion under the curve greater than 11.2. And then we have a little excerpt of the table C. Our chi-squared distributions corresponds to the p-value between 0.01 and 0.02. Again, this is because 11.2 lies between these two values. It's closer to 11.34 than it is 9.84, so we're probably going to be closer to 0.01 than 0.02, but we're between those two proportions. Is there anything I can clarify about the math part of this, the test statistic, or doing the calculation? So then our last part is to make a conclusion. Because the p-value, 0.011, which they got an exact p-value by using the calculator, if you don't have an exact one, using the range is enough. Especially in this case, if it's between 0.01 and 0.02, we know it's definitely less than 0.05. Right? Which is our alpha. We reject the null hypothesis. We have convincing evidence that the birthdays of NHL players are not evenly distributed across the 4 quarters of the year. Right? Essentially, we're stating that we have evidence for the alternative hypothesis. Is there anything I can clarify about the chi-square test for goodness of fit? That brings us to the end of the presentation for chi-square test for goodness of fit. Right, we saw basically the 3 first check marks. We can state appropriate hypothesis and compute expected counts for chi-square test, goodness of fit. We can calculate a chi-square statistic, degrees of freedom, and p-value. And we can perform a chi-square test for goodness of fit using our 4-step process. We will get to how to conduct a follow-up analysis in another lesson. So stop the sharing of the screen. All right, so that is the lesson, essentially, right? Tomorrow we will be doing a Desmos activity to help practice doing these things, right? Basically the first 3 check marks there. We'll get an opportunity to do expected counts, find a calculated chi-square statistic, degrees of freedom, p-value, all that fun stuff tomorrow. And again, like I said, the rest of the resources for Chapter 11 I'm hoping to have done by the end of the week, so you'll have access to all of the stuff for Chapter 11 at that point. And if you have any other questions, comments, or concerns, you can let me know now while we're still in the meeting, or send me a message later, and I am happy to help. Other than that, have a wonderful rest of your day, and I will see you all tomorrow.